Welcome. Dear learner, we are discussing about the radioactive equilibrium. In previous lecture, we discussed about the ideal equilibrium. The equilibrium in which the activity of a parent is equal to activity of a daughter, then such type of equilibrium is the ideal equilibrium. Friends, in this lecture, we have to see what is the secular equilibrium or what is the permanent equilibrium. The equilibrium in which the parent live extremely longer time than the daughter, then such type of equilibrium is known as the secular equilibrium or permanent equilibrium. The parent live extremely longer time than the daughter, and therefore we can say that the half-life of a parent is very greater than the half-life of a daughter. Okay. Also, we can say that the decay constant for a parent is very less than the decay constant for daughter. This equation represent the decay process is carried out very longer time for parent atom. Okay, we know that the number of radioactive nuclei for daughter atom, it is N2 is equal to lambda 1 into N0 divided by lambda 2 minus lambda 1 in bracket e raised to minus lambda 1 into t minus e raised to minus lambda 2 into t. This equation represents the number of radioactive nuclei of a daughter atom. Now, when we take common e raised to minus lambda 1 into t from this term, we get number of radioactive nuclei for daughter, that is N2 is equal to lambda 1 into N0 e raised to minus lambda 1 into t in bracket 1 minus e raised to minus lambda 2 into t divided by e raised to minus lambda 1 into t divided by lambda 2 minus lambda. Now when this term goes from denominator to numerator, it became positive. And when we take common negative or take outside from the bracket, this can be written as N2 is equal to lambda 1 N0 e raised to minus lambda 1 into t divided by lambda 2 minus lambda 1. This term can be written as 1 minus e raised to minus in bracket minus lambda 2 minus lambda 1 into t. Okay. Actually, lambda 1 is a plus when it goes from denominator to numerator, but this sign is a negative. Due to this sign, negative sign, this is a positive. Okay. Lambda 2 is a negative. Okay. So we represent like this. Now, according to law of radioactive decay, we know that the radioactive nuclei disintegrate exponentially with the time, and therefore we can say that number of radioactive nuclei for parent, that is N1 is equal to N0 e raised to minus lambda 1 into t. Okay. When we put this term here, we get N2, it is equal to lambda 1 remain as it is, N1 divided by lambda 2 minus lambda 1 in bracket 1 minus e raised to minus lambda 2 minus lambda 1 into t. Okay. So we can represent like this. Now multiply above equation on both sides by lambda 2. Multiply both side by lambda 2. Okay. And therefore we get n2 into lambda 2, it is equal to, here is a n1 lambda 1 into n1 into lambda 2 divided by lambda 2 minus lambda 1 in bracket 1 minus e raised to minus lambda 2 minus lambda 1 into t. Okay. Now this lambda 1 into n1 goes from numerator to denominator, then it goes from RHS to LHS. So here n2 lambda 2 divided by n1 lambda 1, it is equal to lambda 2 divided by lambda 2 minus lambda 1 in bracket 1 minus e raised to minus lambda 2 minus lambda 1 into t. Okay. This represent n2 lambda 2 means the activity of a daughter. n1 lambda 1 represent the activity of a parent. Okay. Now here the lambda 1 is a very less than lambda 2, or simply we can say that lambda 2 is a very greater than lambda 1, and therefore we can say that n2 lambda 2 divided by n1 lambda 1, it is equal to, here lambda 2 divided by lambda 1 is very small and therefore neglected. So here is only lambda 2. 1 minus e raised to lambda 1 is very small and therefore neglected. We get lambda 2 into t. Again lambda 2 divided by lambda 2, so it cancels. So n2 lambda 2 divided by n1 lambda 1, it is equal to 1 minus e raised to minus lambda 2 into t. And therefore the activity can be controlled by its own decay constant, that is lambda 2. The activity of a daughter can be controlled by its own decay constant, that is a lambda 2. But after very long time, this term e raised to minus lambda 2 into t is negligible, and therefore we can say that n2 lambda 2, it is equal to n1 lambda 1. That is the activity of a daughter, it is equal to activity of a parent. But this is happen after very long time, because this activity is controlled by the decay constant of a daughter, and after a very long time this term is negligible, and therefore we can say that the activity of a daughter, it is equal to activity of a parent. But this is only when after a long time. Okay, so this is related to the circular equilibrium. If we consider one example, that is SR 90, 38. Okay, that is the strontium. Okay, there is a beta decay of a strontium. Okay, that is a beta decay process, and if we consider the half life, it is equal to 28 years. Okay, it is converted into yttrium, that is Y9039. Okay, so it after uh, 28 years, it is converted into yttrium. Okay, and after 64.9 hours, 64.8 hours, this yttrium is converted into zirconium. Okay, zirconium 90. Okay, 40. Okay, which is a stable product. Here, if we observe this example, this SR90, okay, we know that when there is a beta decay, here is also beta decay, the mass number remains same. The atomic number is increased by 1. So here is a 38. Due to beta decay, it became 39. Okay. Here is a 39. Due to beta decay, it became 40. The mass number remains same. So it is here is 90. Here is 90. Here is 90. This is a parent and this is the daughter. The parent live extremely longer time than the daughter. It is about 28 years. After 28 years, it is converted into Y90. That is yttrium 90. But only 64.8 hour, this Y90 is converted into zirconium, that is Z90, okay, which is a stable end product. Okay. From this we can say that the parent live extremely longer time than the daughter, and such type of equilibrium is known as secular equilibrium. Thank you.